Hello and welcome back to Let's Code Physics. We've had some fun looking at our pendulum model here, but there's only so much you can do with a single pendulum. We had some fun with the driving force. We got some neat, little loopy patterns in the phase space plot. But basically, when you have a single pendulum, it's going to follow that same trajectory, right? It's going to end up hitting a limit cycle. Life gets really interesting when you attach a second pendulum onto the first, the scenario that we call the double pendulum. So what I'd like to do today is take our single pendulum code and expand it to be a double pendulum code. We already have some of the basics set up, the visualization, the graphs, etc. But we're going to need to update the differential equation. For one, it's going to have to return to us a value of theta, a differential equation for theta for the first pendulum, and then a differential equation for theta of the second pendulum. So that'll take a little bit to implement. And those differential equations are a lot more complicated than these terms are here. So what I'd like to do, rather than sit here and rederive it for you, I'm going to use an internet resource here. So this is from Josh Altick at, it doesn't have the university on there, but it looks like from here it's Comenius University. So thank you for that, Josh. So here's the basic idea of the double pendulum is that you've got a single pendulum like you would usually have, and then you attach to that one another pendulum. So this rod L1 is free to rotate about this angle. This rod L2 is free to rotate about this angle. But of course, as this one rotates, this one's going to rotate back. So they have this kind of feedback between each other. And of course, there's the gravity acting between them. So the system has what we would call 2 degrees of freedom, your angle theta 1, your angle theta 2. That's going to be important because that's the number of variables that we have to be concerned with. So the way you treat this typically is by using the Lagrange's equation. So for that, you have to set up the potential energy of the system. That's just mgh written in terms of the angles. You have to write the kinetic energy, which gets a little bit complicated once you write it in terms of the angles. It ends up looking like this thing. Then you construct a Lagrangian. The Lagrangian is this weird energy combination because it's not the total energy. It's the kinetic energy minus the potential energy. And there's not really a good, in my opinion, there's not really a good philosophical way of motivating the Lagrangian except to say it's the thing that works in Lagrange's equation. So if kinetic minus 2 times potential was what worked out in Lagrange's equation, that would be what the Lagrangian was. And this is Lagrange's equation right here. This guy, I think, is from a math department, so he calls it the Euler Lagrange equation. I think most physics textbooks just call it the Lagrange equation. But basically, you take a derivative of it with respect to each angle, and a derivative of it with respect to each angular velocity. So you're treating each angle and each angular velocity as if they were separate quantities. And then you take a derivative with respect to time on this one, and basically those two things, this piece and this piece, need to be equal to each other. It's customary to write it as this thing minus the second thing equals 0. When I teach classical mechanics, I like to write this as this piece equals this piece, because you're going to end up moving it to the other side anyway, and it kind of gives you an idea of there's this thing happening in this quantity, and it's the same thing as the thing that's happening in this quantity. And so he plugs it in. He does a wonderful job with his algebra. I'll put a link to this PDF in the description below. You end up with two equations and 2 unknowns. I know it looks like there's a lot of unknowns, but really what you're interested in are the second derivatives. But the problem is there's a second derivative here and a second derivative here. And when you do the same thing, when you apply Lagrange's equation for theta 2, you end up with a second derivative here and a second derivative here. Fortunately, they are linear in those and can be solved to separate the two second derivatives. And so you end up with this monstrosity for theta 1 double dot. You end up with this monstrosity for theta 2 double dot. Now, this is not something you can solve by hand, right? So you can't give somebody this in on an exam and say, here, solve this. This is as far as you can get algebraically. So this is where, of course, a computer program comes in. So what we need to do is start updating or expanding this thing to include theta 1 and theta 2. Now, I think the easiest way to do that, let's see. Gosh, these have so many terms in common. It would be nice, I think, to be able to pass these as... to sort of pass these both forward, to have a single function that calculates all this stuff once. So we're going to call this, let's rename this now, second derivs. And we'll need to call it, let's see, we need to call it theta 1 dot. We'll need to have a theta 2 dot. We'll need to have... let's leave the time argument in there in case we decide to add a driving function. Won't it be fun to add a driving function to this? We'll also need the masses. For right now, let's see, I've already defined the mass up here, so I can call the mass in here when I need to. Oh, it occurs to me, I had this defined incorrectly. This needed to be divided by mass, didn't it? Oh, well, we'll just say the damping coefficient sweeps in the mass. I mean, it's an independent parameter, so it doesn't really matter. Although I suppose I need to go ahead and call these as mass 1 and mass 2, even though I'll keep them the same for right now. So we'll make these identical for right now. So let's have mass 2. We'll just say it's equal to mass 1 for now. There we go. Cool. Alrighty, and I suppose for consistency's sake I can define pi up here. There we go. Awesome. Okay. Let's see, this is now the differential equations. So let's see here. So we're going to call theta 1 double dot, and now I need to take this thing and plug it in here. Now, there are some things that occur over and over again. For example, sine theta 1 minus theta 2, cosine theta 1 minus theta 2, sine theta 2, etc., sine theta 1, etc. So here's what we're going to do. We're going to define some stuff. So here's where we're going to calculate frequently used stuff. The reason we want to do it now, the reason we want to calculate it here and then access it later is so that the computer isn't having to evaluate the same cosine over and over again. It saves a little bit of computer time. So let's just call them cos 1 equals cosine theta 1, cos 2 equals cosine theta 2. It'll also make the writing a little bit easier. Sine 1 equals sine theta 1, sine 2 equals sine theta 2. And then we have the differences. I think he has it always written as 1 minus 2. Is that right? 1 minus 2, 1 minus 2, 1 minus 2, 1 minus 2. Good. All right. So we'll have sine 1, 2 equals sine of theta 1 minus theta 2. Because if it were ever flipped, we could just use the even and odd properties of sine and cosine to rewrite them in terms of what we already have. It's just would cost us a minus sign. Let's see. They also have up here the sum of the masses. I don't see the difference of the masses anywhere. So we'll define something up here. M total mass 1 plus mass 2. And I need to update my comments. Mass of pendulum 2. Mass, total mass. There we go. Cool. Are there any other combinations that I need to, that I'll be frequently using? I see it's got M, L, and theta 1 dot squared a few times. But I'm wondering if that occurs frequently enough to worry about it. M2, L2, theta dot 2 squared. Now I'm a little bit curious as to whether, because this is the same thing as this here. And this one doesn't match that one down there. Let me check this guy's algebra really quick. Let's see here. So theta 1 double dot should have an M2 L2 theta dot 2. It does have an M2 L2 theta dot 2. Okay. And from, let's see, from this one, it should have an M2 L1. Should have an M2 L1 theta dot 1, M2 L1 theta. Okay, yeah, that's supposed to be there. Okay. It's just, it's always nice to inspect equations that have this sort of asymmetry there. Like this is 2 mixed with 1, but this one doesn't have a 2 mixed with 1, but it looks like it works out. Okay. So I see there's a cosine squared there twice. I think that's all right. We can do a square twice. Okay. So let's have a theta 1 double dot. Let's see, I've got a negative M2 L1. Oh, I need to define their lengths as well. So let's have a length 1, length 2 equal to length 1, length of pendulum 2. Get my equal signs aligned, keep my PhD advisor happy. Kevin, if you're watching this, I'm keeping my equal signs aligned, except here I'm not. There we go. Theta 1 double dot. So I've got a negative mass 2 times length 1 times theta 1 dot squared. Theta 1 dot squared times sine 1, 2 times cosine 1, 2. All right, so I've got an M2 L1 theta dot 1 squared sine 1, 2 cosine 1, 2. M2 L1 theta dot 1 squared sine 1, 2 cosine 1, 2. All the negative sign in front. Okay, cool. Then we're going to add to that this piece. Let's actually make this a little bit more pleasing on the eye by putting in some line breaks. Plus, you know what? Can I copy and paste this? Ooh, I can. That makes it easier. Plus equals, so this is going to be grav times, I just have to change his variables to mine. Wonderful. Sine, oh look, it got a theta. I wonder what happens if you run this thing with a theta character in there. I will try that later on. Sine 2 times, this is going to be cosine 1, 2. There we go. And then we've got 2 more terms to add on. So we'll have a theta 1 dot dot plus equals. I wonder if you can fit this whole thing on one line within the screen. Oh my, I got some errant carriage returns. Okay, maybe I don't like doing that so much. That's going to confuse me. All right, so I got a negative mass 2 times length 2 times sine 1, 2. You know what? There is a better way to do this. Thanks to Windows. You don't say that very often. Sine 1, 2. Okay, cool. So negative mass 2. Oops, I missed something. Now I'm glad I changed that. Negative mass 2, length 2, theta 2 dot squared times sine 1, 2. Okay. Theta 1 dot dot plus equals minus m tot times grav times sine 1. And then I need to do all of that, because this is all in the numerator, divide by this thing. So I need to do theta 1 dot dot. Is there a divide equals? I don't know. I'd rather not get myself a debugging nightmare by putting that in here. Length 1 times m tot minus mass 2 times length 1 times cosine 1, 2 squared. Okay, let's do, oh wait, I can adjust this, can't I? There we go, get myself a little bit more viewing room there. All right, let's do a little bit of a check here. So I got negative mass 2, length 1, theta 1 dot squared, sine 1, 2, cosine 1, 2. I got plus grav mass 2, sine 2, cosine 1, 2. Here I got negative mass 2, length 2, theta 2 dot squared, sine 1, 2, negative m total, gravity, sine 1. Then here I've got everything divided by length 1, m total minus mass 2, length 1, cosine 1, 2 squared. Okay. So I'll just take a little break from that. Because guess what we get to do next? Same thing for theta 2 dot dot. All right. So we've got a theta 2 dot dot. It's going to equal, it looks very, I'm kind of tempted to just copy and paste and make the changes as necessary. Do I dare? Do I dare? Yes, I dare. Copy, paste. Okay. Yeah, that's good pedagogically, because then I show the similarities, right? So this one's got a positive instead of negative there. It's a mass 2. It's going to have a length 2. It's going to have a theta 2 dot squared. Again, a sine 1, 2, and a cosine 1, 2. Okay, this is now going to be theta 2 double dot. In fact, let's go ahead and change all those. And please, if I make a typo and you know a copying error, please let me know. We'll get that fixed. Plus g. I got the gravity. This is getting multiplied by m total. Now he moved the mass over there this time. Interesting. Must be a mathematician thing. Grav, at least he's working with units, right? Grav mass total sine 1 cosine 1 2. So this is the gravitational field. My mass total sine 1 cosine 1 2. Okay, cool. And then I've got plus, now this one also has mass total. Mass total. Okay, this is where the symmetry must get restored between the 1s and the 2s, is from all these mass totals. There's a length 1, there's a theta 1 dot squared, right? So I've got the mass total, I've got length 1, and I've got theta 1 dot squared, and I've got sine of 1, 2. See, there's all this nice symmetry between them. And then I need to subtract from that m total. Now this is the same thing as this, basically, except for theta 1 and theta 2, and he rearranged the order. Interesting. So we got a mass total, gravitation, sine 2. There we go. Theta 2 dot dot. Now I divide the whole thing by length 2 times mass total minus mass 2 length 2 cosine 1 2 squared. All right. Let's double check that. So I've got an mass 2 length 2 theta 2 dot squared sine 1 2 cosine 1 2. Good, good. Plus gravitational field m total cosine 1 2 sine 1. Plus mass total, length 1, theta 1 dot squared, sine 1, 2, and then I've got a minus m total, gravity, sine 2. Divide by length 2, mass total, minus mass 2, length 2, cosine 1, 2 squared. All right. Take a little break from that accomplishment. Cool. So, thank you, Josh. Altic, let's get this guy back over this way so I have a little bit more viewing room. Okay, cool. And now I need to return these two. So I need to return second derivatives. And what I'm going to do is I'm going to call this, I'm going to make this into a list. So we're going to say that second derivatives equals a list made of theta 1 dot dot and theta 2 dot dot. So we'll call this one store results. Cool. And now what we need is, what I'd like to do now is get the rest of the code set up. We'll run it once, and then in the next episode we'll take a look at some of the results. So I need this to be a theta 1. I need this to be a theta 1 dot. And let's make that a 0 just for numlock, just to make it easier on ourselves. And let's put these folks out at the same angle. That way they start out like, because I need 3 points. They start out like this, and well, we'll see what they do. So I got theta 2 and a theta 2 dot. Okay, cool. We'll need to call this theta 1. Theta, actually, let's make our phase space theta 2 versus theta 1. Well, let's leave the name for right now so that I don't have to. Actually, let's just get rid of this one altogether because I'd be more interested in the phase space plot. Oh well, no. Tell you what, I'll worry about the visuals next time. Let's just see if we can get the animation running this time. Let's call this Bob 1 and Rod 1, and I'm going to get rid of the access point because that's not going to, or the reference point because that's not going to be as significant right now. Let's see here. There we go. And then we'll have Bob 2 and Rod 2. Now the positions need to be a little bit different because this needs to be Bob 1 dot position minus this vector because it needs to treat Bob 2 needs to treat Bob 1 as the origin. And let's see here. This will be length 1, length 2. Oh, this needs to be length 1, length 1. Okay, Rod 1 is fine. Rod 2 needs to have a position of Bob 1 dot pause, so it'll start there and go to Bob 2 dot pause. Bob 2, Bob 2. I'm sure I'm missing others somewhere, which I will find when I get compiler errors. Cool. Let's see here. So here's what we're going to do. Let's call theta dot dot equal to what did we call this thing? Second derivatives, and it needs to be a function of all of this stuff. Copy. No, I don't need that colon. I'll remove that just a sec. There we go. Oh, I never set up my oh yeah, I did set those up. There we go. And I'm calling time. Cool. And so what we'll do is for theta 1 dot, all I have to do now is access this list. So basically it's calling this function, it's returning a list, and then storing that list under theta dot dot. So I just have to call this as theta dot dot of 1. Theta 1 equals theta 1 plus theta 1 dot times dt, and then we do the same thing and replace the 1s with 2s. So all the messiness, all the differential equation messiness is hidden up there in the differential, in the second derivatives function. Here in the Euler-Lagrangian method, all it cares about is give me a number for this rate of change, give me a number for this rate of change, and I will carry it forward. That's the nice thing about the modular programming. Length 1 sine theta 1, length 1 cosine theta 1, that one can stay the same. Rod 1 equals Bob 1 dot pause. And now we have to do the same thing for the second pendulum, for the new guy. Bob 1 dot pause, Rod 2 dot pause, Bob 2, Rod 2, there we go. It needs to equal Bob 1 dot pause plus this. I did have plus earlier, right? Or did I make it minus? That needs to be a plus. My bad. Bob 1, that would produce really weird animation. Let's see here, and then this can be 2, 2, 2, and 2, and there we go. Let's see here, Rod 2 dot, let's see, I actually need to update Rod 2 dot position to be Bob 1 dot pause, and then I need Rod 2's axis to be Bob 2 dot pause minus Bob 1 dot pause. And I think I need to fix that up here as well. Yes, I do. So this needs to be Bob 1 dot pause minus this. That was the relative vector between them. Other way. 2 minus 1, 1 dot pause. Cool. And then I need to update the graphs. Let's see here. What did I rename this one? I did rename this one to theta 1. And let's call that one time and theta 1. Let's call this one theta 2 and theta 1. Yep. Cool. Well, I'll rename. Well, I may as well rename the variable now anyway. So let's call this phase space. Copy end. Phase space. Cool. All right, let's see what errors I made. Oh, name theta is not defined. I knew I'd missed one. Line 57. 57. Yep, there it is right there. That was in line 60. Oops. Well, I need to fix that one too. I changed the length, forgot to change the thetas. Theta, F5. Name Bob is not defined. Sorry, Bob. Bob.pause. X equals Bob1.pause. Are there any other Bob dots? Oops. Are there any other Bob dot somethings? Only in a comment. Awesome. F5. Nope, Bob2 is not defined. What? Oh, this should have been left at a Bob1. Excuse me. There we go. Global linked 1. Oh, brother. Linked 1. Length. Any others? No? How about a linked 2? Yep. Same spot. All right. F5. Index list out of... Oh, right. Because this thing starts counting at 0 like a weird person. All right. There we go. Lisa's making down there. Oh, cool. We've got 2 pendulums. They are swinging. They are swinging strangely, methinks. That is not the way those are supposed to be swinging. Or is it? All right, there is a way to tell whether this thing is behaving properly. Yeah, see that doesn't look right. That doesn't look natural. There's a way to tell whether this is behaving properly, and that's to check the total energy of the system, which we will do next time. So on the next episode, we'll open with checking the total energy of the system, and we'll use that to narrow down where the typo is. Although I'm sure you've let me know by now in the comments where my mistake is, but I got to get to work, so we're going to call this episode to a close. So thank you so much for watching. I will see you next time. Bye-bye.